Now, binding energy applies to many different kinds of situations. We are, for this topic here, mainly interested in the nucleus, of an atom, where there are protons, and there are neutrons. The neutrons together, and the meaning of binding energy in this case is the energy needed to separate all the protons and neutrons from each other, right? To pull them all apart. Now, in order to I'll just write this now. Energy to separate all the protons and neutrons. Okay. So that's one of the things that I would talk about. Now, the next thing that I would talk about, which are closely related to the binding energy, is E equals to mc squared. By now, a very famous, well-known equation. The E equals to mc squared refers to the property that if we can somehow change the mass of something to energy, then the energy that is given out, or that is changed, that comes from the mass, is given by this formula, mc squared. And let me just write down the words that describe this relation. It is called the mass energy equivalence. Or we can call this the mass energy equivalence relation or equation, which means that if I have a certain mass, then it's equivalent to an amount of energy which is given by mc squared. Okay. So this topic here, in this topic, the connection between the mass energy equivalence and the binding energy is that the binding energy would correspond to an equivalent mass and vice versa. Okay, which means that if I separate all the protons and neutrons in a nucleus, or maybe not all, maybe some of them, or if I bring some protons and neutrons together and fuse them into a nucleus, in any case, if there are changes in energy, there would be a corresponding change in the mass. Okay, so to introduce this idea more clearly, I'm going to start with some everyday examples, just to be sure that we know what all these terms actually mean. I'm going to start with something as simple as the Earth. So let's say that's the Earth. That's our Earth, and suppose that there is a person standing on the Earth. Now, in this case, we can actually talk about the binding energy of the person, right? Binding energy of the person to the Earth. Now, what do we mean by the binding energy in this case? It's the same idea as I described just now for protons and neutrons. It's the energy needed to remove this person from the earth. Okay, what do we mean by removing the person from the earth? It means that we somehow move this person away from the earth until he's so far away, that he or she does not experience any more attraction, any more gravitational attraction from earth. So far away. So that's when he's actually removed. Right, sort of like far enough so that there's no more gravity from the earth. So this corresponds to pulling protons and neutrons apart far enough so that they don't want to combine with each other anymore. So they don't attract each other anymore. And the amount of energy needed to bring the person away, alright, very far away, we can even say to infinity, infinitely far away, would be the binding energy. We can call it the binding energy. Okay. Now, but if you recall my earlier videos on gravitation, you will know that this situation is familiar. We have already learned how to find this energy to move the person all the way to infinity. It's simply the work done. It's simply the work done against the gravity, and there's actually a formula for it. That formula is U equals to minus G mm over R. Okay, where in this case R is the distance of the person from the center of the earth, big M is the mass of the earth, small m is the mass of the person. And this actually is the potential energy. Now to be precise, this formula, this potential energy, refers to the work done to bring the person from infinity to the earth, or to distance r from the center of the earth. Okay, but binding energy is the energy needed to remove the person from the earth. So it's opposite. The binding energy is like the opposite of the potential energy, and because of the attractive force, the potential energy has a minus sign, because the work that you need to do to bring the person from infinity to the earth is negative, in the sense that you don't have to do the work, but the work is done by the earth. So, and that means that in this case, for this example, the binding energy should therefore be plus of G m over R. Right? To write down the binding energy, we have to change the sign of that. Right? Simply because instead of bringing the person from far away to earth, we need to think about bringing the person from the earth to far away. So this therefore is the binding energy. The magnitude of the potential energy is actually the binding energy of the person on earth. So let's press on. Now, let's now think about this in terms of E equals to mc squared. E is equal to mc squared. How would E equals to mc squared come into this picture? Well, when we bring the person from earth to infinity, we have to do work on the person. And this work done is would mean that the potential energy of the person increases by this amount, by the amount of the binding energy. So by moving the person to infinity, there is an increase in energy of the person. That energy is potential energy. So this increase in energy, according to E equals to mc squared, means that the increase in energy has a mass. The energy increase has a mass. Energy has mass. Okay, and equivalent mass is given by this formula. So to actually see what this means, I'm just going to do a quick calculation, right, to clarify this idea. Now, but one thing that I need to do first is to be careful that the mass of the person m here is not it's not the same as the m here. This m is the equivalent mass of the energy increase, whereas that m here is the mass of the person. So to just to clarify this, I'm going to add a little subscript there to remind myself that the mass is a different mass. Okay. So let's see what we mean. Let me start by trying to calculate a value for this binding energy. So how can I do that? Well, I can just use this formula. Let's say the person, let me just take some example values just to get an idea. Let's say the person has a mass of 50 kilogram. Now we can look up the mass of the Earth and its radius. The mass of the Earth would be 5.97 times 10 to the power of 24 kilogram. Okay, and the radius would be 6380 kilometer. So right, and G here, okay, right, takes a bit of searching, sorry for the delay. G is 6.67 times 10 to the minus 11 in SI units, right? I shan't write out the full units in this case. 10 to the power minus 11. Okay. Just to write this out more clearly in SI units. Okay, so I believe that we have all the numbers that we need for this calculation. G is this number, mass of the Earth is here, mass of the person is 50 kilogram, radius of the Earth is this value. Okay, so remembering to convert kilometer to meter is SI units, we can substitute into this formula and find an answer. And the answer is 3.124 times 10 to the power of 9 joules. Okay, so that looks like quite a big amount of energy to bring the person all the way to infinity. We'll probably need a rocket or a space shuttle to do that. Right, so coming back to this mass energy equivalence issue, as I was saying, when we move the person to infinity, there is this the potential energy of the person increases by this amount, which I've just calculated. So the question now is, what is the equivalent mass of this amount of energy? And I can find that using E equals to mc squared. That would be my E. So what I want to find is, what is the mass of this amount of energy? So using E equals to mc squared, I can just rearrange that. M is equal to E over c squared. I put the E into the c, this number into the energy here, and C, right, what is C? C is 2.998, or we can just take it as roughly 3 for a rough answer, 10 to the power of 8 meters per second. Okay, so we have the number for C, speed of light, and the value for E, the energy increase. So putting those numbers into here, let's see what we get. Get 3.5 times 10 to the power of minus 8 kilogram. Now I did a quick search on the internet. I found this interesting Wikipedia website about orders. I'll just write it down here in case you're curious. Orders of magnitude, an important topic in physics, you remember from one of my first videos. Orders of magnitudes for mass. So this wiki page gave the typical masses of different things, from very big to very small. And guess what kind of things would have a mass of this value? An eyebrow hair. Alright, the mass of an eyebrow hair is about this massive. So just a very tiny increase in mass. Okay, if the person is moved from the Earth's surface all the way to infinity, it doesn't really have to be infinity, just far enough so that the Earth's attraction is really weak, then the increase in potential energy of the person means that the mass of the person would actually increase by this amount, by about the mass of one hair on the eyebrow. Okay, so that's what we mean by the this mass energy equivalence, the E equals to mc squared, that the mass of that person would actually increase. So if we measure the mass of the person somehow when he's that far from Earth, we would find, and if we have an extremely accurate instrument to measure his mass or her mass, we'll find that the mass would have increased by this tiny amount, actually increased. So it's a real effect that is understood in physics today.